Welcome everyone. Today we're going to be looking at just a lot of the terminology we're going to be using for the kind of the upcoming sections. And so we're going to see how do we describe the graph of a function. We're going to see a lot of the terminology that comes with this. And over the next few lessons, we're going to see how this relates to derivatives and second derivatives. So we're going to see how this all relates to calculus. But right now we're just kind of introducing the framework here. And so the first definition we're going to consider is, what does it mean for a function to be increasing or decreasing? And so we say that a function is increasing on an interval if the graph of that function just continuously rises as x goes from left to right. So the way to think of this, well, we'll kind of describe it with inequalities, and then we'll also just draw a little picture. What happens when we have an increasing function is that if we take two inputs, x1 and x2, and x1 is going to be smaller than x2. So if we have these two inputs, what happens is when we plug them into the function values, if x1 is smaller, then the function value of x1 is going to be smaller. So what happens is the function, if our function's increasing, it kind of preserves the inequality that's there. So again, if x2 is the bigger input, well then f of x2 is going to be the bigger output. And we can think of decreasing as sort of the opposite. So what happens with a decreasing function is that as we read from left to right, the graph is falling. It's moving down. So with inequalities, we can think of this as if we take two inputs, x1 less than x2, what happens is the smaller input becomes the larger output. Or if we have a larger input, that becomes smaller. So what happens is that a decreasing function almost reverses the inequality. So again, if x1's the smaller input, well then f of x1 is going to be the bigger output. And so graphically, what does it look like to have an increasing or decreasing function? Well, increasing follows the general trend of moving up. So essentially, an increasing function is going to move up as we read from left to right. So it's going upward. A decreasing is just the opposite. So when we look at the graph, it's going to have a downward trend. So it's moving downward. All right, so that's going to be kind of a key feature when we look at functions, is if we look at a function, is the graph moving upward or is it moving downward? And so we can figure this out looking at a point by kind of looking at the tangent lines. So let's try this little example. We're going to determine if these graphs are increasing, decreasing, or neither at x equals c. So in the first one, we have our function. And if we find x equals c, we draw the corresponding point on the graph, and then we can draw in the tangent line at that point. And so if we draw in the tangent line, we see that the tangent line it's moving upward. It has a positive slope. So that means our function is going to be increasing. So our function here is increasing at x equals c. tangent line has positive slope. Now, if we look at the next one, well, actually, we'll come back to that next one. Let's look at the one on the left here, or all the way on the right, rather. Let's look at this one. So again, we're interested at this point at x equals c. So we find the point, and we're going to draw on our tangent line. So let's draw in what we think our tangent line is going to look like. So I would say something, maybe not quite that. Let's try again. Maybe a little. There we go. So I'd say roughly that's our tangent line at this point. And what we see is that the general trend here for this tangent line is downward. So what that means is our function is decreasing at x equals c here. And our tangent line has a negative slope. And we can tell it's negative because as we go from left to right, it's decreasing in height. So it has a negative slope. All right, so we've seen an example where the function is decreasing. We have a negative tangent line slope. We've seen an example where the tangent line has a positive slope, so our function's increasing. And the last example, the last one here in the middle, what happens is if we draw the tangent line, our tangent line in this case is completely flat. So here's our tangent line here. And so in this case, when the tangent line is flat, the graph is neither increasing or decreasing. So it's neither at x equals c. And that's because our tangent line has a zero slope. So what's going on here with our graph is that momentarily, just for a brief moment here, as we're reading from left to right, the graph flattens out. So at this point, it's not really increasing or it's not really decreasing. It's just kind of almost like it's stationary. So it's just kind of flat there. So our tangent line has a zero slope. All right, so this is going to be kind of a key feature that we want to look at. Given a curve and given a point on the curve, being able to quickly kind of draw in the tangent line and identify, is that tangent line going up or is it going down or is it flat? And so something special happens at those flat points where the graph kind of flattens out. And what can happen is our function can have what's called a relative maximum or a relative minimum. And so we're going to define these, make these two definitions here. So we say we have a relative maximum point where the graph changes from increasing to decreasing. So this is almost like it's a maximum point. So it's almost like a mountain peak on our graph. And we see an example right here. So this function has a relative maximum right here at x equals c. So this is a high point on our graph. You know, if we were standing at this mountain peak, it would be downhill in both directions. And so what we're seeing is that if we go a little bit to the left of x equals c, our function is increasing over here. And then if we go a little bit to the right, our function is decreasing on the other side. And so when we have this switch from increasing to decreasing, we have what's called a relative maximum. So it switches right here at x equals c. Now, if the opposite happens, so if we go from decreasing on one side to increasing on the other side, like we're seeing here, and we have that switch right at x equals c, well, this is called a relative minimum. and this is essentially a low point on our graph. So this is like a valley. So if you were standing at this point on the curve, it would be uphill in both directions. So that's a low point. Whereas with a maximum, if you were standing at that point, it'd be downhill in both directions. And so we call these two kind of extremes, we call them relative maximums or relative minimums. We might also call them local maximums and local minimums. So that's just another way to indicate this. So I might say local max, local min, or in general, we might just call these local extreme points. All right, so this is going to be another key feature, and one that's going to be especially important once we start talking about optimizing functions. The whole key to finding the optimal value here is going to come back to these two definitions, relative max and relative min. And so another kind of situation is we might have not just a relative max. So relative max and relative min, these are just kind of local. So relative maxes and min, these are just local. The key word here, the way to think of this is kind of localized. So once we get far away from these relative max and min points, the function might get bigger, it might get smaller, but we're just talking right around. We're just talking nearby. X equals c. So when we talk about local or relative, we're just looking right around x equals c. But once we move further away, then our function might get bigger, it might get smaller. We're only looking right around. We're just looking in a small little area around x equals c. Now, what can also happen is we can have something called absolute maximums and absolute minimums. And this is the largest or the smallest value our function ever takes. So an absolute maximum is the largest value that our function ever takes on its domain, and the absolute minimum is the smallest value. And so what can happen with these absolute maxes and mins is they can occur at a few places. They can occur at endpoints, or they can occur at relative maximums and minimums. So those are kind of the two places where these absolute high points or absolute low points can occur, either at endpoints or at our local maxes and mins. And so the tricky thing that we're going to see is that a function doesn't necessarily have to have an absolute max or an absolute min. It may have both. It may have one and not the other, or it may have neither. And so that's going to be the kind of the tricky thing. How do we figure out where does our function have an absolute max and an absolute min? Well, let's just look at a couple examples here, and just to get a little practice. So in this graph over here on the left, what we're seeing is that we have two endpoints for our curve, but the absolute max, the highest point ever on our curve, so we only have this section of curve and then it ends, and it has two endpoints there. The highest point occurs at x equal to -1, and the value is 5. So this is our absolute max point. The value of our function here is the y-coordinate, and it occurs at x equals -1. Now our absolute min, what's our absolute min value? Well, this is the lowest point on our curve. And we see that the lowest point on our curve, remember, we only have this section, and then it kind of starts and stops at those endpoints. And the lowest point on our curve is right here. So the value is the y-coordinate, and it occurs at x equals 3. So the absolute min value is 1, and it occurs at x equals 3. So what we're seeing here is that our graph has two endpoints, a left endpoint and a right endpoint. And then it has a relative max, and it has a relative min, these high and low points, and they just happen to be also the places where our function has its absolute max and its absolute min. Now we can have, let's look at the next one. We can have a situation where, again, we have a relative max, we have a relative min, we have one endpoint now, and what we're seeing is that this endpoint is higher than that relative max, and this is actually the highest point that our graph has. So in this case, our absolute max is going to be this, the absolute max value is going to be the y-coordinate, so 6, and it occurs at x equals 5. So the max value is 6, and the x-coordinate tells us where it's happening. So it's happening at x equals 5 here. Now, we do have this low point here at x equals 3, but if we keep looking on our graph, eventually, over here, we get lower than it. And the way we kind of read this is if it kind of just trails off, we really read this as the graph keeps going. And so what happens is on this section, all of these points over here are eventually lower. They're eventually smaller than this relative min. And so in this case, there is no absolute min for our function. If I were to think, say, one of the points over here was the absolute min, well, if this keeps going, if that was my absolute min, eventually I'm going to get lower than it. And it keeps getting lower and lower. So none of the points over here are going to be an absolute min because we can always just keep going a little bit further and you have something smaller. All right, so in this little example, we're seeing that the absolute max happens at an endpoint, but then we don't actually have an absolute min. And so we're going to investigate this further, and we're going to see how to actually kind of go through and calculate, using derivatives, help us locate where these different maxes and mins might occur. So right now we're just kind of introducing the terminology here. And then one last thing we're going to be looking at is how does the slope of our function actually change? And so there's kind of two ways it can change. We can have the situation where our graph lies above the tangent lines. So here we have some tangent lines, and then we have the graph of our function drawn in. And when we look at this, the tangent line, or the curve, is actually sitting almost on top of that tangent line, just slightly above. So you can see it just slightly bend above the tangent line. And what's going on here is the slope, as we read from left to right, the slope here is actually increasing for our tangent lines. So For this one right here, this is kind of a small positive slope. And then over here, we have a large positive slope. So what's happened, as we read from left to right, we've gone from having small positive slopes to larger positive slopes. So our slope here is actually increased from left to right. Now, the opposite can happen. If we're looking at our curve and we draw in some tangent lines just to see what's going on, well, another option is the graph of our function can sit below the tangent lines. And that's what we're seeing here. The curve kind of bends below the tangent line. And really what's going on is our slope is decreasing. So what we have here is, here we have a small negative slope. And then as we read from left to right, we go from a small negative slope to a larger negative slope. So we've gone from a small negative slope to a larger negative slope, so our slope has actually decreased. We've gotten more negative. And so there's kind of two options for what can happen when we look at curves. And this is called the concavity. So we say that a function is concave up if the graph lies above the tangent line near x equals a. So the slope of the graph is increasing. And we say that our graph is concave down if the graph lies below its tangent line. So you want to think of this concavity as like the shape of our graph. And so there's a few options for what a concave function can look like. So let's look at concave up. And a lot of times I'll abbreviate this with like CU or CCU. And so what a concave up function looks like is it has the way you can think of this is it's concave up like a cup. So it has this almost U shape to it. Or it might just be part of that U shape. So it might just be like the left side, or it might just be like the right side. So you might have just something like this or something like this. Maybe just one of those sides. So concave up functions are always going to have this sort of shape. Concave down is going to be kind of the opposite. And I'll abbreviate these, CD or CCD. And the way these functions or way these curves look is, you can think of it as it's just upside down. Almost concave down like a frown, if you want a little rhyme there. But it's an upside down U. And it might not be the full thing. It might only be like half of this. So it might just be the left side, or it might just be like the right side of this. So concave down, you might have the whole thing. So you have that whole upside down U shape, or it might just be one side, or it might just be the other side there. And so the way to think of concavity is this really describes the shape of the graph. It describes how the graph of our function actually bends. So if we had an increasing function, so if we had our tangent line, the tangent line kind of gives the general trajectory of where our function's going. What concavity does is it tells you how the function actually bends. So if that's our tangent line, well, you can have the curve actually bend above, which gives you an increasing function that's concave up, or the curve can bend below, can kind of underperform the tangent line, and that's concave down. Or if we had a decreasing tangent line, so something like this, concave up would bend above the tangent line, and concave down would bend below. So those are that's kind of what concavity ends up doing, is it describes how the function, the shape of the function, how it actually bends relative to the tangent line. So concave up kind of bends above, concave down kind of bends below. And so the last special feature we're going to consider is, when do we change? When does the shape of our graph change? And we call these special places inflection points. So these are the points on our graph where the function changes from being concave up to concave down, or vice versa. So in the first little example here, in this section right here, our graph clearly has that concave up shape. Over here, our graph clearly has that concave down shape. And so what happens, kind of gets a little hard to tell what's going on right in here in terms of the shape of our graph. And we're going to see how we can actually pinpoint this location here with some calculus. But what happens is we make this transition going from concave up to concave down at one specific point. And we call that our inflection point. So it might look something like that. In the next example here, we might have we have one side that's concave down, and then the other side has that concave up shape. And again, we see what we're seeing here right in the middle is, it's kind of hard to tell exactly where it happens, but this side is definitely concave down, this side is definitely concave up, and we're going to see that there's going to be one point right there in the middle where this transformation happens. We change concavity, so we have an inflection point right there in the middle. Same thing over here. On one side, our graph is that concave down shape. On the other side, we have that concave up shape. And so again, it's kind of difficult right here in the middle to tell exactly where this is going to happen. But there's going to be one point where we're going to have this change in concavity. And so when that change happens, we call that an inflection point. And so one little thing here about the definition for inflection point, we're only going to be considering inflection points where our function's continuous. So again, continuity means there's no jumps, breaks, or holes in the graph. So no jumps, breaks, or holes. All right, so this is kind of all the terminology. So there are a lot of definitions here, but these are all the different things we're going to be talking about over the next few weeks when we start to see some applications of how we can use derivatives, first and second derivatives, to investigate the behavior of our function, and then ultimately use that to solve some optimization problems. All right, so we're going to stop there, and next time we're going to see, where does the first and second derivative come into all this? So we'll see you then. Bye-bye.